Great pleasure for me to introduce Professor Brigant. She is from University of Paris. She's an expert on statistics of manifold, machine learning, and differential geometry. She's going to talk about clustering using the Fisher-Rao metric. So please, Professor Brigant.
Thank you. Very sorry for this technical problems. So yes, I'm going to talk about clustering probability distributions with the Fisher-Rao metric. So this is joint work with Stephen Preston, Stéphane Pechmerel, and Nicolas Guilou. Next slide, please. Yes. So the goal that we pursue is to perform learning on the space of probability distributions. So we consider a space of probability distributions, and in the space, each point is a distribution. So why do we want to consider probability distributions? Well, we can consider the example of a medical application where we have a data set, where each data point is a set of measurements corresponding to one patient. And maybe a correspondence between measurements across patients does not exist, maybe because we don't have the same number of measurements for each patient. And so we don't have a common representation space for each of our patients. And so a possibility is to consider the distribution of the measurements instead of considering the vector of measurements themselves. And so for one patient, we have a histogram, and we can fit a probability distribution on this histogram. And so this is a data point. Okay, so what do I mean by learning? What type of learning do I want to do? Simple learning tasks, such as clustering. For example, dividing our data set of measurements for a group of patients into diseased and healthy. We might want to do regression. So let's say that we have not, for a single patient, we may not have just one set of measurements, but we have one set of measurements for each time. So then we have a time varying distribution. And we might want to interpolate between these histograms using regression. And we might want to do PCA or etc. Okay, so which tools can we use to perform learning on the space of probability distributions? Well, we need to be aware that the space of probability densities is not a vector space. So if F1 and F2 are two probability densities, their sum no longer integrates to one, so it's no longer a probability density. However, it is convex, and so we can still use the L2 metric to compute linear interpolations and linear mean. So here I give an example of a linear interpolation between F1 and F2, where F1 and F2 are Gaussian distributions. And we see that the linear interpolation is bimodal for all t, except for t equals 0 and t equals 1. And in particular, the linear mean is bimodal. And so we can imagine that for certain applications, this will not be very satisfactory. We would like to have an interpolation that stays unimodal all the way, and even maybe stays Gaussian all the way. And so the L2 metric, at least for some applications, will not give natural interpolations and means, not what we want. So what we can say is that the space of probability distributions can be seen as a differentiable manifold. So depending on the context, either in the non-parametric framework, then we can consider infinite dimensional manifolds of probability densities. But we can also want to work in the parametric framework, and then we will deal with finite dimensional manifolds. So in the parametric framework, we deal with probability densities with respect to a fixed measure. They are parametrized by a certain parameter theta that belongs to an open subset of Rd. And this open subset of RD is a d-dimensional manifold, and any density can be represented by its parameter in this manifold. So for example, the univariate normal Gaussian model, any normal distribution can be represented by mean and standard deviation in the parameter space, which is just the upper half plane, where you have the mean on the x-axis and the positive standard deviation on the y-axis. Okay, so if we have a differentiable manifold, then a natural idea to perform learning is to equip the manifold with a Riemannian metric. There are two main approaches to do this in the literature. There is optimal transport using Wasserstein metric. This is non-parametric. It's a non-parametric distance between distributions, can be seen as a Riemannian metric. And there's the other approach is information geometry based on the Fisher-Rao metric, which has both a parametric version and a non-parametric version. And we will be focusing on the parametric framework and the information geometric approach. Okay, so the outline of my talk is this. I will first present the Fisher-Rao metric and how to do geometric statistics using this Fisher-Rao metric. Then I will present two works, if I have the time. The first is based on the geometry of Gaussian distributions for applications in air traffic control. And the second is the study of the geometry of other distributions, non-Gaussian, so beta and Dirichlet. Okay, so first for the Fisher-Rao metric. In information theory, the Kullback-Leibel divergence is often used to compare distributions. It measures the quantity of information lost when using one to approximate the other, but it's not a distance. In particular, it's not symmetric. So if we want to make it, if we want to have a real metric, a real distance, what we can do is use the Hessian of the Kullback-Leibel divergence instead. This is given by the Fisher information. So more specifically, given a parametric family of probability densities, F parameterized by a parameter theta, what we have is that the Kullback-Leibel divergence between the density F at theta and the density F at a small variation, at a small perturbation of theta, is given by this formula where we have the Fisher information I of theta that appears. So this is the Fisher information matrix. It's a D by D matrix where D is the size of my parameter vector. Next slide, please. So the Fisher information matrix, it's symmetric, positive, semi-definite, and so it can be used to define a scalar product. So two increments d theta 1 and d theta 2, I can compute the scalar product between the two by putting here the information matrix. Now here I see that this scalar product depends on the foot point theta, so it defines a Riemannian metric, a family of scalar products on the parameter space. And this was first suggested by Rao in 1945. So for two tangent vectors, this is how we compute the Riemannian metric. Then the Kullback-Leibel divergence can be approximated by 1/2 of the squared norm of d theta for this Fisher-Rao metric. The Fisher-Rao metric is invariant to diffeomorphic parametrization change, so it doesn't depend on the way that we parameterize our statistical family. And it's also invariant to transformation of the statistical model by a sufficient statistic, and it's actually the only one up to a scaling factor. So now that we have the Fisher-Rao metric, what can we do? Well, we can do anything we can, all the things that we can usually do in a Riemannian manifold. We can compute angles and norms of tangent vectors. We can compute lengths of curves just by, how can we do that? So we look at a curve gamma of t in the parameter space. At each point gamma of t, we get a velocity vector, gamma prime. We can compute the norm of this velocity vector using the Fisher-Rao metric. And we can integrate this norm in time and get the length of the curve. And then the distance between 2 points is the length of the shortest curve linking the 2 points. And under appropriate conditions, the distance is given by the length of geodesics, of minimizing geodesics. So these shortest curves are geodesics. They are generalizations of straight lines. And their length gives us the distance. Sorry. Next slide is, yes, geodesics give us optimal interpolations between distributions. So here on this picture on the left, we see a geodesic in the parameter space of normal distributions, and on the right, we see the corresponding optimal interpolation between the densities. Okay, so let me just give an example, the example of the univariate normal distributions, which is, I think, the first parametric family to have been studied, the Fisher-Rao metric on this family was the first to be studied in the 80s. So here, as I said, the parameter space is the upper half plane. Here, I forgot to write it, but this is from a paper by Costa and co-authors. This is a picture from a paper from Costa and co-authors. Here we have 4 Gaussian distributions. They can be represented by these 4 points in the parameter space. And so the Fisher information here is this 2x2 matrix, and it gives the following metric. So here, if you disregard the factor 2, which is not very important, in the numerator you have just the Euclidean metric, except you divide by the square of the y coordinate, and so this makes the metric non-Euclidean, and it actually gives you the Riemannian metric of the Poincaré half plane. So it's a well-known Riemannian geometry. It's one of the models of hyperbolic two-dimensional geometry. So here, yes, thanks. The geodesics, what are they? They are half circles orthogonal to the x-axis, and so we understand that it's cheaper to go from A to B. It's cheaper to follow these half circles than to go in a straight line because of this division by the y component. So we have closed form expression for geodesics, analytic expression for the distance. And we can also try to have an intuitive understanding of this distance by noticing that here, the distance between the distributions A and B is larger than the distance between C and D, because the length of the geodesic, we can see it's longer. And this reflects in some way, this can be interpreted as reflecting the fact that the densities A and B have less mass in common than C and D, because the standard deviation is lower. On the contrary, if we wanted to use Wasserstein here, Wasserstein distance between normal distributions would give us Euclidean distance in the parameter space. So for the Wasserstein distance, the distance between A and B is the same as the distance between C and D. It's no longer true here. So it depends on what we want, but yeah, that gives us some intuition. Okay, so many parametric families have been studied in the literature since the 80s. I've made a list here, probably not complete, but we are going to see later. I'm going to present something on beta and Dirichlet distributions. Okay, so before we move on, I just want to say that now that we have a Riemannian structure, we can adapt learning algorithms to the Riemannian setting by replacing the Euclidean scalar product with the Riemannian metric. straight lines with geodesics, and using the exponential map and the logarithm map, etc. So I won't spend too much time on this. I just want to mention that we might need to replace the Euclidean mean with another mean that is called the intrinsic mean, or the Fisher mean. So what is that? It's actually defined in any metric space. So the intrinsic mean of n points in a metric space is defined to be the minimizer of the sum of the squared distances to the points we want to average. This is a weighted sum. Here I put the same weights to everyone, but we can have different weights. So this is defined in any metric space. And in general, it's not unique. In a Riemannian manifold, what is nice is that we have conditions for unicity. We have conditions depending on the injectivity radius and the curvature. And also, it can be computed using a gradient descent algorithm that is based on geodesic computations.
So you need to not have too negative curvature, right? So the problem with that so the conditions that you're talking about are related to, you don't want it to be too many places with too much negative curvature. Is that correct?
Yes. Well, I mean, no, you want your injectivity radius to be bounded, but no, in negative curvature, in fact, everything it works fine.
You don't want something like that, right?
You don't want if you have a Hadamard manifold, which is negatively curved and geodesically complete, then you have unicity.
Okay.
But if you have positive curvature,
you're right. So if I'm on the circle, I can have the 2 points here, which don't make it unique, to make the mean unique, right? So if
if you have the North Pole and the South Pole, then the whole equator will be
Thank you.
will be minimizers. Yeah. Okay. So this brings me to say that the learning performance depends on the data manifold geometry. So the fact that minimizing geodesic always exists, that depends on geodesic completeness, and unicity of these minimizing geodesics and of the mean depends on several things, and notably on the curvature, on the sign of the curvature. Okay. So now let me talk about my first work. So this is about using the geometry of Gaussian distributions for an application in air traffic control. So the multivariate normal distributions in general is quite hard. I mean, it's is not as easy as the univariate case because we don't have analytic expressions for geodesics nor the distance. So we have to use numerical solvers. But if we look at the centered normal distributions, then everything has closed form. So here the parameter manifold is the space of covariance matrices, so the space of symmetric positive definite matrices. We have non-positive sectional curvature, and the distance is affine invariant, and it's also called the affine invariant distance on the space of SPD matrices. So it's also a distance that is used outside of information geometry. Okay, so we want to apply this to complexity-based clustering of air traffic. So the French airspace is divided into sectors, which are dispatched to teams of air traffic controllers. And in the design of those sectors, we need to make sure that the workload is equally balanced between the sectors. So complex areas must be kept small. So, for example, where near airports or large towns. And low complexity areas, for example, where you have small density of aircrafts or simple structure of traffic, that can be made larger. So the goal here is to be able to automatically characterize the local complexity of the air traffic situation during a certain time lapse. So as in the images here. So the traffic situation is given by positions and velocities of the planes that are present in the airspace during the considered time window. So here we don't take into account the altitude, so we just have vectors in R2, because altitude is treated separately in air traffic control. So we have these positions and velocities of planes. In each point, in each point where we have a plane, we look at a neighborhood, and we have a certain distribution of velocities of other planes. And we assume that this spatial distribution is Gaussian, and we estimate its mean and covariance matrix with these Nadaraya-Watson estimators. So basically here, we are going to be interested in the covariance matrix. We do a weighted sum of V transpose, of the velocities V transpose centered, using a kernel, so a truncated Gaussian kernel, for example. And this gives us an estimator of the covariance matrix. And this covariance matrix can be seen as representing the local disorder around xi. So it gives us this dispersion of the velocities in this area, the velocities of the plane trajectories. And we're not so much interested in the mean, we're more interested in this dispersion. And so we discard the means, and we choose these covariance matrices as complexity indicators at each point. So we do this at each point where we have data, and then we obtain a point cloud in the space of SPD matrices, so 2 by 2 SPD matrices. So in other words, we obtain a point cloud in the space of centered bivariate normal distributions, and we perform clustering on these distributions using the Fisher-Rao metric. So how do we do that? We use an online k-means algorithm. So we initialize, what we want to do it's summarized in the image, maybe it's going to be clear in the image. We have an input image here where we have so here you can see the plane trajectories where the color represents speed. But basically here we have points and velocities. At each point, we estimate a covariance matrix. We end up with a point cloud in the space of SPD matrices. We perform clustering in this manifold using the Fisher-Rao metric. And this gives us a clustering of the air traffic situation. So online Riemannian k-means, so basically we initialize cluster centers, and it's an online algorithm, so we process the observations one at a time. And for each new observation, we find the cluster center that is closest for the Fisher-Rao distance, and then we move it in the direction of this new observation, following a geodesic. So it's basically the same as in a vector space, but we use the Fisher-Rao distance, and instead of following straight lines, we follow a geodesic. So we use the exponential map. Okay, so we obtain a clustering of the air traffic into zones of homogeneous complexity. So some remarks. This can also be seen as an optimal quantization problem, which is, so a clustering and optimal quantization are different ways of seeing sort of the same problems. I'm mentioning this because the paper that we wrote on this presents this problem as an optimal quantization problem, but it can be seen both as clustering and quantization. So in order to reduce dependence on initialization in the algorithm, what we do is that we repeat each step a certain number of times. Using a result of Silver-Bonabel of 2013, we can show that the algorithm converges if the points, so here the covariance matrices, if the points are assumed to be drawn from a compactly supported measure on a manifold with injectivity radius that is bounded from below, And since here we're in a manifold of negative curvature, we have no problem with the injectivity radius because it's plus infinity. So in negative curvature, if you have a compactly supported measure, then it's fine. Okay, so in practice, what we did is we just chose 3 clusters because empirically, generically, we noticed that then the cluster centers could be ordered then in the sense that A is greater than B if A minus B is positive definite. This is because the Fisher-Rao metric sorts the covariance matrices by rank. So basically, the three clusters correspond to matrices that have two eigenvalues that are close to 0, or one eigenvalue close to 0, or two eigenvalues that are far from 0. And this is what gives us the 3 levels of complexity that we observe in the results. If we do the clustering using the Euclidean metric, we don't see this anymore. So on the next slide, you can see results for the Fisher-Rao metric and the Euclidean metric. And so we see that the crossings belong to a certain cluster that corresponds to high complexity, and then simple trajectories or parallel trajectories are clustered into a low complexity cluster. Okay. So now for the last work I wanted to present, I wanted to talk about non-Gaussian distributions. So in particular here, beta and Dirichlet distributions. So beta distributions are defined on 0, 1. They have a PDF that is parametrized by 2 positive reals, x and y, which gives us a wide variety of shapes, as you can see on the left. They are used as probability distributions on a probability P, and they are also conjugate priors to binomial distributions in Bayesian statistics. So we see that we have the gamma function in the PDF, and this means that when we compute the Fisher information is computed using the Hessian of the log of the PDF. So we get derivatives of the log of gamma. And this, the derivatives of the log of gamma are called polygamma functions. They are special functions. So psi and the derivatives of psi are called polygamma functions. And so they appear in the metric here. We see that here, what is our beta manifold? The parameter space is the positive quadrant, so x and y positive, equipped with this quadratic form here. Okay. So we can try to compute the geodesics by computing the geodesic equation. So the geodesic equation, how do we get it? Geodesics are locally, at least, length minimizers, but they're also the curves with 0 acceleration. That's why they really generalize straight lines. So this equation, nabla gamma dot equals 0, says that the acceleration is 0. And so how do we, this is basically, we can compute this using derivatives of a metric. And it gives us, we can see it gives us a second order differential equation, which is not particularly nice at all. We can see that the coefficients here are pretty nasty. And to our knowledge, this does not, we don't have closed form solutions for these geodesics. But we can solve these numerically, either for an initial value problem. So I fix initial position and initial velocity, or a boundary value problem. I fix initial position and end position. So this we can do numerically. We can solve the geodesic ODE. So here on the left, there's the geodesic in the parameter space and the corresponding optimal interpolation between the PDFs on the right. And on the far right, we have geodesic balls in the parameter space. So what are these? At each center, so here we've plotted so the center of the ball and then geodesic rays that have all the same length. So this means that it's the same cost to go from the center of the ball to each of the end points of the rays. So this means that it seems to be less costly to go along lines that go through the origin, and this can be explained by the fact that these lines are the lines of equation y over x equals constant. These corresponds to all the distributions that have the same mean. So it's less costly to go from one distribution to another with the same mean. I'm going to skip the rest. So this is what we can do numerically. Now, theoretically, what can we say about this manifold? Even though we don't have closed form for geodesics, maybe we can say something about the geometry. So what we can prove is that the space of beta distributions equipped with the Fisher-Rao metric has everywhere negative sectional curvature. So sectional curvature, it's defined for any two-dimensional subspace of the tangent space. So at each point, I have a tangent space, which is a vector space, and I can look at any two-dimensional subspace and compute its sectional curvature. It generalizes the Gauss curvature of a surface in R3 in the sense that if you consider a two-dimensional subspace of your tangent vector, intersect it with a ball, you get you get a neighborhood, two-dimensional neighborhood. And if you project it on the manifold using the exponential map, you get a two-dimensional submanifold of your manifold. And this is a surface, and you can compute the Gaussian curvature. And this is what sectional curvature is. We have a formula when we have basis vectors for sigma. We have a formula for the sectional curvature generated by sigma, depending on the curvature tensor, which basically depends on derivatives of the metric, and depending on the metric again. So in dimension 2, we only have one sectional curvature to compute at each point because the tangent space, is already of dimension 2. So only one sectional curvature to consider at each point. So here it's the case, we're in dimension 2 because we have two parameters. So our parameter space is of dimension 2. This is the formula we get for the sectional curvature. So here the polygamma function psi, they are completely monotonic. This means that psi is a function where each derivative, the derivatives are alternatively positive and negative. So we know that the psi prime prime is negative. So we know that this in front, the term in front is negative. And what we need is we need to know what is the sign of what is inside the parenthesis. And it turns out that this we got for free from a result by Yang that comes from a paper on these special functions. So it's a paper on polygamma functions from 2017. And this paper says that this function is subadditive, which means exactly that that this quantity in parentheses is always positive. So this means that we obtain sectional curvature that is negative everywhere. Okay, so can we generalize this to Dirichlet distributions? I won't spend too much time on this, but Dirichlet distributions can be seen as generalizations of beta distributions. Instead of being defined on 0, 1, they're defined on the simplex of any dimension. We have in the figures here, you have example of Dirichlet of samples on the two-dimensional simplex. On the next slide, yes, this is the main result. We were able to show that the space of Dirichlet distributions equipped with the Fisher-Rao metric is geodesically complete and has everywhere, just like the beta distributions, negative sectional curvature. And since it's also simply connected, it's what we call the Hadamard manifold. And a Hadamard manifold is basically the closest to a Euclidean space that we can get. It's the manifold where everything is works sort of like in a Euclidean space. So I won't go through the elements of the proof because I don't really have time. I'm just going to say that we have several sectional curvatures because we're in dimension greater than 2, so the proof is a little bit more, is very different from the two-dimensional case. So the consequence of this is that the Fisher-Rao manifold of Dirichlet, and in particular the Fisher-Rao manifold of beta distributions, are Hadamard manifolds. So any 2 points can be linked by a unique minimizing geodesic. The Fisher mean is unique. And so algorithms based on distance and barycenter computations are well defined. So for example, the Riemannian k-means is well defined. What is Riemannian k-means? It's the same as the Euclidean k-means, except you replace the distance by the geodesic distance, and you replace the Euclidean mean by the Fisher mean. So let me just, before I stop, let me just show you some simulations. So here we have a very simple example. On the left, you have the parameter space, and on the right, you have the PDFs. So here I chose beta distributions that are in the parameter space that are on 3 different lines. This means that, so on each point on the same line corresponds to distributions with the same mean. Beta distributions with the same mean. So it seems like we have 3 clusters corresponding to the 3 different means. The Fisher-Rao metric sees that, whereas the Euclidean metric doesn't. Of course, this could be very well, this is easy to fix. In this very simple example, it would be enough just to renormalize the parameters, and the Euclidean metric would work very well. So let me show another example, a little bit more, little less simple. Okay, so here I have generated ellipses in the space of parameters. So we have basically 2 main clusters corresponding to 2 different, approximately to 2 different means, but we also have difference in shapes. We have PDFs that have a mode in 0 or 1, or we have PDFs that have mode inside of 0, 1. And so it seems natural to cluster them exactly like the Fisher-Rao metric does in these 4 clusters shown here, depending on the mean, but also the shape. The Euclidean metric doesn't do, this is a very different clustering. And if we renormalize the parameters, so that's the next slide, this is what we get. And finally, the next slide is Wasserstein metric. So we can do k-means with the Wasserstein metric in this case, because in 1 dimension, the Wasserstein metric is just an L2 metric between quantile functions. So it's also possible to do k-means with the Wasserstein metric. But here, the Wasserstein metric doesn't distinguish the shapes of the PDFs like the Fisher-Rao metric does. Okay, so I don't know if the last slide here is a medical application where we applied this to medical data, where we have, so this is the example that I spoke of at the beginning of the talk. We have, for each patient, we have a set of measures. And what we do is that we fit a beta distribution on these measures so that each patient is represented by a beta distribution. So we have 2 data sets. The first one, the measures correspond to area strain of the right ventricle to assess cardiac function. And the second one, the measures correspond to cortical thickness to diagnose Alzheimer's disease. In the first data set, we have the same number of measures for each patient. So here it's less pertinent, it's less obvious that we want to use distributions. But on the second data set, we have different number of measures for each patient because the measures are regularly made on the cortex, and the cortex size varies from one patient to another. So this means we have different number of measurements for each patient. And in this case, using distributions can be interesting. So for each patient, we have a beta distribution. So our patients can be represented by point clouds in the parameter space. And we perform supervised and unsupervised classification in the parameter space and try to look at performances to compare Euclidean and Riemannian performance. And Riemannian does well, better than Euclidean, and sometimes it does almost as well as if we used the original Euclidean data when we have it, even though we have reduced the dimension by a lot. Okay, so I will stop here. So to conclude, we have seen that we could apply Fisher-Rao geometry of normal distributions, beta distributions, but we also could try to apply the geometry of Dirichlet distributions, and we have tried to apply it to text classification in link with generative text models like latent Dirichlet allocation. In this model, each document is represented by a Dirichlet distribution, so it was tempting to try to use the Fisher-Rao Dirichlet geometry on this. However, with the increasing dimension of the parameter space and with large data sets, since we don't have closed form expressions for the geodesics, the algorithms become very slow. So it's possible to do things, but it's on very small data sets, so it's difficult. Nevertheless, if you are interested in implementation of these geometries, they are available in an open source Python library called geomstats, which has an information geometry module where the different geometries I spoke of are implemented, and also others. So feel free to take a look. And thank you very much for your attention.
So thank Professor Brigant for the great talk. Maybe we have time for one quick question.
I have a question. Can
Yes.
you hear me?
Yes.
Yes.
But I'm not sure it's quick. So
Well, then no, because I have to run another building. The next event starts in 10 minutes.
I see.
Yeah, if it's quick, yes, but otherwise that
I'll try to get a quick answer.
It's not very quick. I
very
would
quick.
say.
So maybe we'll reserve that for email exchange. I have the same problem with the longer question, so I'll keep it. But so
wait, Alessandro, how many minutes do you have till the next?
Oh, 5 seconds.
5 seconds. Ah, okay.
Yeah.
So,
Difficult. Okay.
So let me close the. Let's thank Professor Brigant again for the great presentation. And so let's speak resume with the last event in 10 minutes from Helmke, where there's going to be a panel discussion. And so I'll see you guys again there. Okay.
but can I stay here and ask Alice